Good afternoon. I am Almudena Márquez. My talk is titled Lee Point Symmetries and Conservation Laws for a Nonlinear Viscoelasticity Model. The work is done with Professor Bruzón. We are both from the Department of Mathematics of the University of Cádiz. The presentation is divided this way. Firstly, we present the equation we are going to study. Then we are going to find the Lie point symmetries of this equation. Afterwards, using the Lie point symmetries, we are going to obtain symmetry reductions to reduce the equation. Then we also going to obtain conservation laws of this equation. And finally, we give some conclusions. Firstly, we consider a nonlinear viscoelasticity model. The simplest model for viscoelasticity is the Hooke's law, but it's really simple. So as we know, viscoelasticity materials have like memory because they have rheological properties. So here we are going to consider in particular the Kelvin-Boyd model, and is also considered in many studies the Maxwell model. So as we said, we consider a generalization of the Kelvin-Boyd viscoelasticity equation, which is this equation. It's a partial differential equation where we have time t in R, the real numbers, and x in an open subset of R. Then we have u, that is a real value function, C and B, which are different to 0, and F, that we are going to consider as a non-linear function. So we are going to apply the classical Lie method to obtain the Lie point symmetries. This method reduces the independent variables of the partial differential equation. So we obtain an ordinary differential equation, which will be easier to solve. So here we have some reference about textbooks with the theory of this method. So what's the idea of the classical Lie method? The idea is that we have to require that the PDS is invariant under a group of transformation. So here we have the group of transformation. And to be invariant, it means that we have to apply the invariance condition, which is written here, where we have x3, the third prolongation of the operator x, and x is the infinitesimal generator. So applying this condition, the third prolongation, to our PDE, we obtain a system of equations, and solving it, where we use Maple is the software we use, we can give a complete classification of Lie point symmetries. So as we said, with f nonlinear function and c and b different to 0, we have this symmetry. That's a time translation. And then for some particular functions of this, of f, c, and b, we have additional generators. So for example, with f arbitrary function, c constant and b constant, we have also a space translation. Here we suppose b a linear function, and we have another additional infinitesimal, another symmetry. The same way with different expressions of F, C, and B. So we get 7 symmetries for different cases for this PD. So now it's important that we classify these solutions because we have to obtain a set with only one generator from each class of invariant solution. So we don't have one invariant solutions with 2 generators. So there's no repetition. So to do this problem, I mean, is equal to classifying the orbits of the adjoint representation. Okay. So firstly, before the adjoint representation, we are going to define the Lie bracket. So we have 2 vector fields, and the operator Lie bracket is defined this way. So for each pair of vector fields, we obtain its Lie bracket. Once we have the Lie bracket, we can find the adjoint representation, which is defined with this expression. Okay, here we have the Lie brackets. So it's necessary first to calculate the Lie brackets and then the adjoint representation for each pair of vector fields. So doing this applying these 2 expressions, we have the one-dimensional optimal system for our PD. So here we have the set where each element has an invariant solution and there's no repetition. Each one has one invariant solution. So now for each element of that set, we are going to look for symmetry reductions. So we reduce the original PD to an ODE. So to do this, okay, to find the invariant solution, we have to apply what is called the invariant surface condition, which is defined this way. So applying this, we can reduce the original PD to an ODE. For example, for this first element, okay, we obtain this traveling wave reduction, which reduces the original PD to this ODE. In the same way, for the second element of the optimal system, for the third one, all is the same, okay? And for the last 3, also the same. Here we don't put the reduced ODs because of the length of the ordinary differential equation. So with this ordinary differential equation, we can look for exact solutions for the original PD. Now we also construct what is called conservation laws. Okay, is a very important application for physical problems. A conservation law is defined as a continuity equation which describes conserved quantities that do not change in time. Okay, and the method we apply to calculate them is the multiplier method. This method was developed by Anko and Blumen, and here we have 2 references where the method is described. So how is defined this? We have a conservation law for our PD, our equation, satisfies this expression where we have T, the conserved density, X, the conserved flux, and here Q, the multipliers. Firstly, we are going to find the multipliers. Okay, so we have here the expression of the multiplier. And how do we find it? by solving the determining equation that is defined here. Okay, here we have Q, what we want to find, and E is EU is the Euler operator with respect to U. Okay, so solving this determining equation is how we find the multipliers. For this calculus, we use Maple again. Okay, in particular, we use commands refsims, pdsolve, and also the dsolve. So we obtain that the multipliers for our equation with f, the conditions f nonlinear function and c and b different to 0 are these ones. So now, once we have the multipliers, we obtain what's the conservation loss. I mean, the conserved density and the conserved flux for each multiplier we have found. So here we have the 3 conservation laws. Now, conclusions. Well, we have studied a model, as we said, that's a generalization of the Kelvin-Boyne viscoelasticity equation. We have given a complete classification of the lead point symmetries for different expressions of F, C, and B. Okay. Then we have obtained the invariant solutions with respect to the one-dimensional optimal system of subalgebras. So we have one invariant solution for each element of the optimal system. Substituting these results, we have reduced the PDE to an ordinary differential equation, which now are easier to solve than the original PDE. Also, we have constructed conservation laws using the direct method of the multipliers, which was developed by Janko and Blumen. And as future work, as we have reduced the PDE to an ODE and we have several ODEs reduced, we can find new exact solutions from these reduced ODs. So that could be a future work. Thank you for your attention.